Yes, please feel free to ask questions. So yesterday we saw the motivation for the axion from particle physics and also from the dark matter problem. We discussed the production of axions in the early universe, and then we started to discuss axion searches. Actually, we described in some detail the cavity technique for discovering dark matter axions. Then there are a bunch of other techniques that I'll go over, and you'll see. They're kind of varied set of techniques. Next one is solar axion searches. Oh, first, this is in a plot showing where, over time, the cavity searches are most likely to be able to put limits on the coupling to two photons as a function of mass. And these two lines here are the QCD axion, the two models, DFSZ and KSVZ. So solar axion searches can be done by exploiting also the conversion of axions to photons in the magnetic field. So this is somewhat different because the axions from the sun typically have keV energy, and so they are relativistic. And they also convert to photons, but now this conversion is more similar to neutrino oscillations. There's an oscillation length, the inverse of the momentum transfer, because the axion has mass, but the photon has no mass. Energy is conserved, so the momentum transfer has to be provided. The momentum transfer is QZ, given by this formula for relativistic axions. And then the probability of conversion is proportional to the coupling squared, the magnetic field squared, and then it oscillates. And the limit of zero momentum transfer is proportional to the length squared. So several experiments have been done of this kind. The first one was actually done in Brookhaven. Then there was an experiment in Tokyo that took data, and then there's a pretty well-known experiment at CERN called CAST. CAST is a magnet. Actually, it's an LHC prototype magnet that is put on some kind of device that allows one to track the sun as it moves across the sky for some period in the morning and some period in the evening. And so the axions come from the sun, they have keV energy, they convert in the magnetic field, and then there's some X-ray detector at the end that's supposed to see the events. There's also an X-ray focusing device. So this is what it looks like in reality at CERN.
So in the equation that you had for the oscillation, so that's why you were, we were discussing that the magnetic field, it really doesn't have to be homogeneous inside that much, because at the end you will get just a slightly different...
Right, so thank you for this question. Okay, so here the energy is the same for the axion and the photons. The momentum is different. Ideally, you would want to have a magnetic field that varies on the length scale, which is the inverse of the momentum transfer. That would give you that would allow you actually to have a conversion probability proportional to L squared for very long lengths. If you tuned it properly by having the magnetic field vary in the correct way. If you don't do this, is what I assumed here, that the magnetic field is homogeneous, then it will oscillate. It will first go like L squared, but then it will come, the axions will oscillate to photons, then oscillate back to axions, just like neutrinos do actually. is similar to neutrino oscillations.
So for CAS, how many, what is the size of the oscillation set?
This it is the oscillation length. Okay, is okay. Let me think about this for a second. If the mass of the axion is afforded less than an eV, its energy being afforded 3 keV, the oscillation length is longer. The oscillation length is longer than the magnet. However, once you approach 1 eV, then the oscillation length becomes comparable. And then what they do, actually I implied this, and thank you for this question. What they do is they introduce some kind of gas in the conversion region to try and match the axion mass as much as possible to the photon mass. And that allows them to keep the resonance for longer distance. And actually, I can show this, the results they obtained. So here is the result they obtained as a function of axion mass, the coupling that they can exclude above this line. This is actually a limit from horizontal branch stars that extends from left to right for very long mass range. Here, you saw the onset of the finite oscillation length over the length of the gas magnet. But then they introduced helium-3 as a gas, and they are able to postpone, so that they actually were able to enter the QCD axion region for case V axions near about 1 eV mass. They sort of basically touched it for a while. So in the big picture that I have, so maybe I should explain the big picture again. I put here masses all the way down from 1 eV to 10 to the minus, 14 eV. The limit from actually the supernova is roughly 10 to the minus 3 eV. But CAST will say, well, we're not just looking at QCD axions, we're looking at any axion-like particles, and then there's no limit from the supernova, but there's still a limit from horizontal branch stars, because this actually uses the same coupling. So the limit from these two, CAST and horizontal branch stars, is afforded 10 to the minus 10 GeV minus 1. There's a proposal called YAXO to scale up CAST. And so now it's a big thing. I mean, here's a person standing, and it's also expensive. But if it were built, then, so it has actually it has a toroidal magnet similar to Atlas with 8 coils. So the magnetic field goes like this. And then it has X-ray optics and receivers here, X-ray detectors. If it is built, then the limit that they could get is somewhat below 10 to the minus 11 GeV minus 1. And they would be able to run along, actually, the QCD axions for these rather heavy axions.
So why does it have that cutoff at the end there? Why does this go straight across?
Why? Okay, this is the effect that we were talking about. This is the same thing. Yes.
Why don't they just make it bigger?
Well, then it's even more expensive. Yes.
But isn't that's the goal over there, isn't it?
Right. No, you're right. Small steps first. So this thing is going to be already pretty expensive, and so I think they say, I think that the price is not exactly known, but they talk about 50 million to build this. Igor Irastorza at Zaragoza in Spain is the spokesperson, and he makes a very strong case for this. And I would love to see it built. I mean, what's 50 million? It would be great to have it, but okay. So as Priscilla actually already pointed out yesterday, you can look for solar axions by Primakov conversion in crystals on Earth, and this has been done by a number of collaborations. So solar axions coming from the sun, keV energy, can convert by Primakov in the electric fields of nuclei. And this, because keV is of course the distance, but inverse keV is the distance between atoms in a lattice, you can have Bragg scattering. So resonant conversion in particular directions. And this is some slide, I forgot why I took this, but that shows how the counting rate will vary in an experiment in the course of day as the crystal rotates relative to the sun, because it's fixed with respect to the Earth. And there's supposed to be some pattern, and if you recognize this pattern in the signal, in your counting rate, then you can maybe have a discovery or put a limit. So I don't have all the limits, but I think they're all pretty comparable. Maybe actually the best limit is from Dama, because Dama is relatively big and is of this order. So it's actually not quite as sensitive as CAST, for example. People have also looked for solar axions using the axioelectric effect, which is the same as the photoelectric effect, but the photon is replaced by axion. So Dimopoulos and friends calculated the cross-section. It's given by this formula. So this, the axion comes in and it hits an electron, and then the electron is detected somehow. So it's sensitive to the coupling of the axion to the electron, which is actually one of the most model-dependent couplings. The coupling to the photons, also the coupling to the nucleons, are less model-dependent. But you could make models where this coupling is, say, 10 to the minus 3 or something. So various Avignoni et al., Xenon, and Edelweiss have looked for this axioelectric effect. With my apologies if my list is not complete. Probably other people have done this too. Okay, so that finishes solar axion searches. I wanted to come back to the behavior of axion converting to photons. Of course, photons can also convert to axions. So let's consider a photon going into the screen, and there's a magnetic field vertically, and the photon is linearly polarized at an angle. Then what happens is that the component parallel to the magnetic field can convert to axions and then disappear, whereas the component perpendicular to the magnetic field doesn't get depleted in this way. And so there's going to be a rotation of the plane of polarization. Just how much it rotates just depends on this probability of conversion that I had before. Now there's another effect pointed out by the director of CERN and his friends. And that is that actually this component that gets depleted also acquires a phase, because the component perpendicular to the magnetic field propagates like usual. The component parallel gets depleted, but also it acquires a phase because its speed is not quite the same. The speed of light for this polarization is not quite the same as for this. And so there's a phase that appears, and this then produces ellipticity. If you have initially linearly polarized light, it will become elliptically polarized. And this is the formula for this phase. Zavattini was the head of an experiment at Legnaro lab near Padova called Pivilas, and actually it was a very impressive place. I went to visit once. It has this magnet which is quite big, and it was on a platform which was spinning at half a hertz or something. It was so eerie to see this big thing rotating. And it had a magnetic field, it had a laser and going through this magnetic field, and they were just looking at how the laser light gets modified. And actually they thought they had discovered axions, but then later retracted their result. But because they had thought they discovered axions, many people went to do experiments to confirm them or rule them out. Because if they had been correct, you would have been able to do the following: convert photons, say a laser beam, to axions in one magnetic field, with the axion going through a wall, and then they convert back in another magnetic field. This goes by the name of shining light through walls, SLW. So you see, dark matter axions can be detected in a cavity experiment, for example, because the axions are already there. They're provided by cosmology. Of course, you don't know very well how many there are. Solar axions are produced by the sun, but this experiment is completely a laboratory experiment because you produce your axions and then you detect them. So that's a big advantage, of course, if you can do it entirely in the laboratory. But then the rate goes like the coupling to the fourth power, because enters here squared and then here squared again. So usually the rates are relatively small compared to the other experiments. At any rate, various experiments, BME, BVM, and so on and so forth, put limits that soon ruled out the Pivilas claim. Typically, the coupling that is ruled out is of order 10 to the minus 7 or 10 to the minus 8. So on the big picture, these experiments are over here. And again, because of the limited coherence length, they have this cutoff at high masses. So they go like this here. Now, it's possible to actually rather dramatically improve this experiment by doing resonantly enhanced axion photon regeneration. I think this is called also RIPA. So here is your laser producing photons, converting to axions in a magnetic field in the wall, and then you go back. If you put a cavity here, the beam will go back and forth many times, and you will have many more axions actually proportional to the finesse of this cavity. Typical finesse is 10 to the 5 for a very good cavity. But also, you can put a cavity on the other side, and then, provided they're exactly in tune, you will have resonant reconversion. And this again multiplies the signal by a factor of order the finesse. So the signal gets multiplied by 10 to the 10 in principle. And so since you have to take the fourth root of it in the coupling, I guess a factor of 250 in sensitivity in the coupling. This was originally pointed out by Hogerveen, and then we sort of rediscovered this later. There is an experiment of this type being built or planned and built called ALPS-2 at DESY. And it will, when it uses daisy Hera magnets, a long string. I think it's like 100 meters of Hera magnets, and fancy lasers and so forth. And when they're all done, they will be able to do this, more or less. Rule that out, or find axions. So someone asked about microscopic forces mediated by axions. The original paper on this was written by Moody and Wilczek in '84. So axions are light bosons and they mediate a force. So axion exchange produces a force. Now here's the coupling of the axions to fermions. The fermions we're interested in are electrons, protons, and neutrons because they are in material objects. This is the coupling here. The mass of the fermion divided by the axion decay constant. Some number of order 1 expressing the model dependence of this coupling. Then you got normally just I gamma 5 because A is a pseudoscalar. But because the standard model violates CP and P, you can actually have also a much smaller coupling theta F, which is not pseudoscalar but just scalar. But this theta F in the standard model is expected to be of order 10 to the minus 17. It's a very small, is the size of the theta bar induced by CP violation in the electroweak interactions. So this is much, well, these two couplings have different phenomenology because the coupling to, which is scalar, is just a coupling to the number density. The coupling which is pseudoscalar is actually a coupling to the spin density. Both of these couplings have challenges. This one, the difficulty is that the coupling is extremely small. And here the challenge is that if you couple to the spin density, of course, spin density also produces magnetic fields, which are long range. And so you have to screen out the magnetic fields very carefully. But anyway, these experiments have been done of this type by these people. And there are some limits have been put, but they are not very strong compared to the other limits we have been talking about. Arvanitaki and Geraci have proposed a new version of this experiment where you have some object that is spinning, and this object produces axion field by the scalar coupling. And then here you have another object that detects axion fields by this pseudoscalar coupling, which, as I mentioned, is a coupling to the spin. Now, if you rotate this object at just the right frequency, so that the Larmor frequency actually, then the axion field can produce NMR type transitions on the side of the detector here. And this is kind of some kind of a resonant improvement of the previous idea. But it's still very challenging. But I think they are working on this. I think Geraci is working on this. Okay, so now I come back to dark matter detection because we discussed cavity detection, but there are other methods for dark matter detection, axion detection that have been proposed. Here is an idea where you have superconducting wires and you have currents in these wires and they produce some magnetic field. And by controlling the currents in the wires, you produce a particular shape for this magnetic field. And you try to give it just the correct X dependence or Z dependence so as to provide the correct momentum transfer for axion to photon conversion. So it is axion to photon conversion in a magnetic field. The magnetic field is produced by the superconducting wires. The currents in the wires are controlled so that the magnetic field has a particular wavelength so that you can have resonant conversion. And then you can further improve the experiment by putting some confocal mirrors on both sides so the photons go back and forth, and then you can do this, but you have to make it fairly big. I think perhaps as big as this stage here. Anyway, Ripka and Wagner actually and collaborators did a version of this experiment. So here's another idea proposed by Peter Graham, Surjit Rajendran, Dima Budker, and collaborators, is to use nucleomagnetic resonance. So here you have a target of material that is spin polarized, just like in an NMR experiment. It's spin polarized by a magnetic field. The axion I mentioned already, because it's non-relativistic, has a coupling to the spin of these nuclei. And this axion field is oscillating. And so in principle, it could excite a transverse component to the magnetic field. So transverse magnetization excited, just like in NMR, but not by, in NMR it's excited by a transverse magnetic field. Here it is excited by axion field. The gradient of the axion field playing the same role as a transverse magnetic field. And you can have resonant conversion of resonant excitation of the transverse magnetization of this sample when the axion mass equals the Lomoff frequency. And then this can be picked up with a squid. They actually proposed two kinds of experiments, and actually this one is maybe more promising. Here you take again a sample of spin polarized nuclei in some magnetic field. And then you put a transverse electric field. Now what happens is that the axion field will induce, the axion field is oscillating, and it will induce an electric dipole moment on these nuclei. And this dipole moment is oscillating at the frequency equal to the axion mass. The electric field is static, but the dipole is oscillating. And so again, you'll have, like an NMR, you will excite transverse oscillations of this magnetization that you can pick up with a squid loop. This is what they think, the limits they can place on QCD axions and other dark matter axion-like particles. Let me put it on my own graph. Okay, so right. For this, you have to read the text. I'm sorry, I forgot. I'm sorry, I forgot the meaning of the dashed line. The first experiment, they think they can do this well. The second experiment is in principle more sensitive, and they believe they can do this well. And the dashed line, I'm sorry, I forgot. What does it say?
Limit from magnetization noise of the sample for phase 2.
Where should I read, huh?
It's in the middle. It's,
Okay, the red dashed line shows the limit from,
line.
yes, magnetization noise for phase 2. Yeah, I'm sorry. I think I would have to reread the paper to know exactly what they mean about this.
It's going to get to if they do phase 2, and it's set by the noise, the magnetization noise. So that's, I guess, a phase 2 limit. And a solid, the red shaded section is phase 1. Yeah. So they go from the orange to the red shaded, and they go
To the dash line.
red dash in phase 2.
Well, I didn't give them credit yet for the dash line.
What polarized nuclei that have this number?
What is the sample? I forgot. But I think your question is particularly relevant to this experiment, but I forgot why. I'm sorry, I don't quite remember. So anyway, Dima Butker at Mainz is working on this, and he said in 5 years he would have some results. He told me this privately. Here's an idea I wrote a paper on with my colleagues Tana and Sullivan at Florida, which is actually a variation on the cavity experiment. In the cavity experiment, the oscillator is an electromagnetic mode of a cavity. In this version, the oscillator that gets excited is the LC, is the oscillation current in a LC circuit. This is easy to tune. That's certainly a big advantage compared to the cavity experiment because you can just tune an LC circuit with having a tunable condenser. So it is sort of interesting how this works. So you have a superconducting solenoid. It produces a magnetic field that is up. Now you can show that along the field lines of this externally applied field, you have, in the presence of an axion field that is oscillating, you'll have an oscillating current along these magnetic field lines. And it's given by this formula. So it is the time derivative of the axion field times the magnetic field that's applied. What happens is this current is now the source of a new magnetic field. Since the magnetic field lines are like this new magnetic field is toroidal in this volume, and it has a flux through this pickup loop. And then it drives this LC circuit. And there's also a thermal background, and there's a background of magnetometer noise in the squid. But according to paper, these are the sort of limits that could be put with this technique. The limit A is using the ADMX magnet, just putting a circuit in the ADMX magnet. And then this is using the CMS magnet, if we could use it for this purpose. And the dashed line is, if you take the ADMX magnet, keeping the magnetic field the same and just making it smaller or bigger, you follow this line. So the difference between this line and the CMS magnet is 3 Tesla or something, and the ADMX magnet is 8 Tesla. So this perhaps can be done with LC circuits. There is a student of David Tanner named Nicole Chrysosto is developing this technique. So This is another idea that I wrote a paper on. I was a bit surprised no one had ever pointed this out before. If the axion masses of 4 to the 10 to the minus 5 eV or gigahertz, this is of the same order as the hyperfine splitting in atoms. So if you have an atom in its ground state, it can absorb an axion and go to a hyperfine neighbor. If you have an atom and it makes a transition, you would be able to detect this by shining a laser on the atom, which is tuned in such a way that as soon as it makes a transition, it pumps the atom to an excited state, and then the atom comes back down and produces fluorescence. This technique is very well known and apparently is so good that you can count every single transition with nearly 100% efficiency. So this seems like a nice way to detect axions. You can tune, of course, this only happens when the axion mass equals the difference in the energy levels, but you can tune the energy levels with a magnetic field. So you need to have a sample of order moles or something, Avogadro's number of atoms, to have a sufficiently large counting rate, and you need to cool, because you don't want thermal excitations to produce the same effect. So you have to cool basically to millikelvin temperatures to keep all the atoms in this ground state, and then the only transitions are due to axions. I'm very keen on this idea, but I'm a theorist. Experimentalists, they like it, but maybe they think it's a little difficult. But I'm very keen that Eric does this idea, works on this. There's also a group in Padova, Gianni Carugno and collaborators thinking about this, and a group in South Carolina around Franco Avignone and Robert Creswick thinking about this. What is the temperature?
Yeah, how much do you have to cool it?
Millikelvin. Actually, 10 millikelvin, more or less. It depends where you are. Now, you can do this using either the coupling to the electron or to the nucleus. I had mentioned before that the electron coupling is more model dependent, but that experiment is simpler, actually. It's easier to do the experiment with coupling to the electron spin. And actually, I was amazed by how well this works. I mean, it's maybe not easy to actually do, but on paper, you can easily get to QCD axions. And also, you go there in a region of 4 to 10 to the minus 4 eV. There's no competition in this region, or very little competition on how to do this. So this may be a good approach to axion dark matter detection. And this is the limit that you can obtain with coupling to nucleons. It's a little bit more difficult for nucleons, and it's not, here it goes flat. For nucleons, it bends up this way. Now, I was pretty conservative in how much mass you can cool to millikelvin temperatures, but Franco Avignone came by and he told me he cools quarry, which has a mass of order 700 kilo, to 10 millikelvin. And that is almost 100 times more mass than I assumed. I assumed 10 kilogram to 10 millikelvin temperatures. So in principle, this thing can be done. Okay, but relatively little work has been done in this direction. So there's something that makes me happy about all this is that if you take all the techniques together that I described, actually you can cover most of this range. First, atomic transitions at the top near 10 to the minus 4 eV. Then cavities. Of course, these are have the ones that are the best, most developed and the most mature technology, around 10 to the minus 5, 10 to the minus 6 eV. The LC circuit around 10 to the minus 8 eV, and NMR techniques at even lower masses. So in principle, you can detect QCD axions, dark matter axions, all over the plausible mass range, all the way from 10 to the minus 3 eV to 10 to the minus 12 eV, at which point the Peche-Quinn scale has gone up to the Planck mass, and we don't think it should go any higher than that.
Where the coupling with the electrons enters here?
Oh, okay, thank you. So I put here GA gamma equivalent, because of course they're not all the same coupling. So some are to electrons, some are to nucleons, some are to photons. I just ignored the differences that are supposed to be of order 1, with the caveat that the coupling to electrons may be much less than 1.
Because if we assume that is 0, for instance, because that is the model dependent, what region here do you take out?
So here you take out nothing, because this is actually the nucleon coupling that's relevant. Here is the photon coupling that's relevant. Here it is the photon coupling that's relevant. And here it is the electron or the nucleon coupling that's relevant. But here you can do both electrons and nucleons, but electrons is easier job than nucleons. But more model dependent, right. I think you would want to do it with nucleons if possible, right. Okay, so how far along am I?
You have 15 minutes.
15 minutes. Okay. So we covered the first 3 topics. I now want to say that axions are different from other dark matter candidates because they form a Bose-Einstein condensate. So let's go back to the axions produced in the early universe during the QCD phase transition. Their density then at time T1 is the time when they were produced, is of order 10 to the 47 per centimeter cubed. The velocity dispersion is associated with the horizon then, and it's of order 10 to the minus 4 soon after they produced it, so for the 10 to the minus 17 today. These 2 numbers allow you to calculate the phase space density, the density in phase space. And this number is 10 to the 61. It's an extremely degenerate fluid, bosonic fluid, the axion fluid is. This is conserved by Liouville's theorem. So it's 10 to the 61 then, and it's 10 to the 61 today if the flow is collisionless. So it's interesting that we have using 2 different limits of quantum field theory to describe dark matter. And it reminds me, at any rate, of the early days of trying to describe light. Light must have appeared extremely mysterious to the early physicists. Newton described it as a particle flow, and Huygens described it as a wave. And you couldn't tell the difference at the time. You couldn't tell the difference till Young actually showed the wavelength to show that light is a wave. And actually the same is true about dark matter. You can describe dark matter as a particle or as a wave. But I think most people think of it as a particle, but a wave works equally well. So quantum field theory allows, of course, allows both descriptions. It's inherent in quantum field theory. So WIMPs you think of as particles because they are non-degenerate, whereas axions should be described as a wave or classical field because they are in fact highly degenerate. So the first thing which I would like to show is that if you describe the axions as a classical scalar field, it will behave exactly like cold dark matter, provided you're in the non-relativistic limit, of course, and also you can only observe it on distances much bigger than the wavelength. I mentioned that in a galactic halo, QCD axions would have wavelengths of 4 to 10 meters. Of course, when you do cosmological observations, you're averaging over 10 meter scale. So this is somewhat pedagogical exercise, which I think is interesting. So here is the Klein-Gordon equation for self-interacting field, like the axion field would be. And here is how you go to the non-relativistic limit. You map actually the scalar field, which is a real scalar field, onto a wave function. The wave function satisfies the Schrödinger equation. It defines a density, and it defines a velocity. The velocity, if you take the phase of the wave function, take the gradient of the phase and divide by m, that defines a velocity field. The Schrödinger equation produces exactly the same equations as the point particle description if you average over distances much bigger than the wavelength, because they're equivalent to the continuity equation and to the Euler equation in a gravitational field. This is this equation, except it has an extra term due to so-called, which is often referred to as quantum pressure. This Q that appears here is given by this formula. The quantum pressure is there because if you have a pile of WIMPs and you turn off gravity, it will just sit there, right? If you have a pile of axions, you make the same pile of axions. By the Heisenberg uncertainty principle, they will start to flow away because the size of the pile implies a momentum. For the WIMP, this momentum is entirely irrelevant and small, but not for an axion because the axion is so light. So the pile will start to, the wave function will tend to spread. This effect is due to quantum pressure. But in the early universe, if you look at big scales, you cannot see this. If the mass is as large as we think it is for QCD axions of order 10 to the minus 5 eV. If you let the mass change, you can make the mass much smaller, then the effect becomes much more important. Here, the first three terms are the usual equation describing the growth of density perturbations in the early universe. Delta is delta rho over rho. This quantum pressure produces a new term here, over here. And this introduces a Jeans length in this axion fluid, or fluid of axion-like particles. As far as I know, this was first pointed out by these authors, Klopov et al. And Bianchi et al. If the mass is 10 to the minus 5 eV, this Jeans length, which is afforded the size of the solar system, is not observable. But as was pointed out yesterday, if you make the mass very small, for the 10 to the minus 22 eV, then this Jeans length becomes for the 10 to the 22 centimeters, which is 3 kiloparsec. And this has been proposed as a way to alleviate the small-scale problems in CDM structure formation. As far as I know, the first person to point this out is Sanjin Sin, and then many, many other people have written about this, and there have been, even the last few months, have been several more papers. So, we are trying to make a distinction between axions and WIMPs. Axions are a wave, WIMPs are a fluid of particles. The axions have a wavelength. You could make this wavelength very big by taking the axion mass very small, and then you have ultralight axion like particles, and there's many interesting papers about this, but I'm not going to pursue this. Because in fact, I believe there's another distinction between axions and WIMPs, is that the axion field is actually not a classical scalar field, but is a quantum scalar field. And quantum scalar fields differ from classical scalar fields on some time scale, which is actually the thermal relaxation time scale. So if this is the axion field, we believe, of course, it's a quantum field, not a classical field. And it is, if you do its Fourier transform as a classical field, these are classical numbers, but in the quantum theory, these are operators. And the behavior of the quantum system is different from that of the classical system. In particular, as was pointed out by Einstein, the degenerate quantum fluid forms a condensate. So Bose-Einstein condensation. Bose-Einstein condensation occurs when these four conditions are satisfied. You have identical bosons. They're highly condensed in phase space. Their total number is conserved, and they thermalize. Each one of these four conditions is necessary, and the four conditions together are sufficient for Bose-Einstein condensation. When the four conditions are satisfied, you can show that most of the particles will go to the lowest energy state available to them through the thermalizing interactions. So axions are, of course, identical bosons. They're highly condensed in phase space, because I showed that the degeneracy was 10 to the 61, which is certainly highly degenerate. Their number is conserved, but do they thermalize? That is the big issue. In atomic physics, people see Bose-Einstein condensation, but the problem is in a way very different, because atoms thermalize very quickly. And what's difficult to achieve with atoms, to get them sufficiently cold as to be highly condensed in phase space. This condition is difficult to satisfy with atoms, whereas this condition is easy, whereas for axions, this is easy, readily satisfied, and this is a question mark. 5, okay. 5 minutes. So this may be a bit of a surprise. Why do they do this, actually? It's actually a very robust phenomenon. Let's imagine that we have highly degenerate fluid. That is to say, the quanta are in very few states, and those states are very highly occupied, say 10 to the 61 quanta per state. Then, if they thermalize, that is to say, if by interactions between the quanta, they can jump between the states, then they will produce entropy by putting all the quanta in the ground state and putting the remaining energy into a thermal spectrum above the ground state. And this process will produce entropy, and this process is irreversible. So this is a little bit counterintuitive only because we are not used to thinking about identical bosons, because we don't have such experience as children or young physicists. So we'll learn about it in graduate school. Also. The thing about this, if you have 10 to the 61 quanta in the few states, it essentially has no entropy at all. The condensed state has no entropy either. But because you have been able to put the energy here into this thermal spectrum, you will have the entropy of this thermal spectrum. And this has far more entropy than this, and this process is irreversible.
How long does it take?
Well, this is the big question. This is the question of how much time does it take to thermalize, right? So that is the big question. But he only gives me 5 minutes, so.
You have 7.
But no, this is the point. Okay, so I showed that, okay, if they don't thermalize on sufficiently small time scales, the system will behave like a highly degenerate fluid and obey classical field equations. And then, as I showed, they behave like CDM. But if you look at it on a longer time scale, then these particles will Bose-Einstein condense, and now they will behave differently from CDM, because most of the particles will go to the lowest energy available state, and CDM does not do that. Now, if you deform the box, let's suppose that it takes a day to thermalize, and I deform the box in 1 minute. What happens while I deform the box is that you take this state forward in time, ignore this, okay, ignore the thermals, and re-express it in terms of the new modes in the new box. And this evolution is entirely the same as cold dark matter, because it's described by classical field equations. But if you look at the next day, after they're thermalized, these particles will have gone back to the ground state in the new box, and that behavior is not explained by CDM. It's different from CDM. So I like this picture. Well, I think it's sort of a historically significant picture, first of all, where people who did Bose-Einstein condensation in dilute gases, they took one condensate and then another, and then they expanded, and the two condensates overlapped, and they interfere with one another. And I just like this picture because this behavior of interference is entirely classical behavior. But of course, the particles, when they are doing this, they are not in the lowest energy state. They will, presumably, if you could keep them in a similar condition, sufficiently degenerate, after a while, they would go to a new ground state by interacting. So to answer the question that Xerxes posed, what is the time scale over which axion field thermalizes? We look at axion field dynamics. So you can describe the axion system as a set of harmonic oscillators with frequencies omega j, and then interactions given by terms like these, conserving the number of quanta. There are two types of interactions that you can consider. There are lambda 5/4 type self-interactions, and also there are gravitational self-interactions. Lambda 5/4 interactions are like point interactions. They have no if you write them in momentum space, the amplitude has just has a momentum conservation delta function, but no momentum dependence in the amplitude. For gravity, the amplitude goes like 1 upon the momentum transfer squared. So this is the expression for the lambdas for gravitational self-interactions. So actually, maybe this is a good stop. How many minutes have I got?
-2.
-2, okay. So tomorrow, I will want to ask the question, using these interactions that the axons have, how much time does it take for them to thermalize? And is that time longer or shorter than the age of the universe? If it is shorter than the age of the universe, axions behave differently from WIMPs, and we're able to say something. Okay, so thank you very much for...
So we have time for questions. Well, I have one. When you talk about these actions, I mean these actions that Witten likes, it doesn't matter if those are actions, QCD actions or action-like particles, right?
that Witten likes.
Yes, this 10 to the minus 20.
Yes, I don't know how much he likes them. He wrote a paper about them. Yeah, ultralight axions.
So it's axion-like particle, yes, right?
Yes.
It doesn't, it's not related to this QCD axion, or it
Right,
not
so-
necessarily, right?
So the case of QCD axions, the mass depends upon the decay constant. If you bring the decay constant all the way to the Planck scale, the mass of the axion is like 10 to the minus 12 eV, if I remember correctly. So still very far from 10 to the minus 22 eV. As far as I know, there are no good particle physics models for 10 to the minus 22 eV. But what is true is that in string theories, apparently you have many axion-like particles, a whole set of them. And it's usually the masses are not very precisely predicted. So maybe some of them are 10 to the minus 20 eV, but one of them is supposed to be the QCD axion as well. So they are not all that light either. So we don't know very well. We don't know very well.
More questions?
So I have been thinking about the idea of the atomic transitions for the quarry that Frank was mentioning. So they can cool down to 10 millikelvin, right? But then to split the levels, for that they need an homogeneous magnetic field, and that for that large sample of 100 kilograms, that's going to be really challenging, right? To have to try to push as far as possible in the high axion mass. That's going to be.
Yes, but he was not suggesting we're going to use quarry for this, right? I mean,
So he was suggesting that he can cool down a large sample, right?
Yes,
But
yes.
then the issue of the magnetic field that.
right, and you also need, that's right, to have a sufficiently large magnetic field, right? That's correct, yes. Mhm. Yeah.
To keep the energy levels split at the right, or tune at the right action mass, right? So you can sweep over the a certain range.
So you
Right.
need small homogeneities cool.
I think it would be crucial for the tunable laser and the hyperfine the splitting, right?
I guess for the laser probably, but right. You're asking how homogeneous the magnetic field is to be. Right, I think for the laser I'm not, you should trust Eric. Right, probably for the, because it, yes, I guess it has to be fairly homogeneous, right? Because people do make very highly homogeneous field magnets for MRI, right, for nuclear magnetic resonance imaging.
More questions?
This question is from yesterday's talk. What is the QCD horizon?
Why is the QCD?
Horizon.
Why is it an axion? No, sorry, I didn't get it.
What is the QCD horizon?
What is
Horizon.
Or what is how big is it? So the horizon is definition is the size, volume, which is linear size is as big as the h at QCD time multiplied by the speed of light. So at QCD time, the temperature is, say, 1 GeV. The h of the universe is 10 to the minus 7 seconds, and the horizon is 60 meters. The significance of this that beyond 60 meters, you cannot have causal contact between regions further than 60 meters ordinarily. Of course, inflation does provide a way around this, but ordinarily, without inflation, you could not have causal contact over distance scales bigger than the horizon, and that's 60 meters at QCD time. Yeah.
More questions? I have one, the last one. If the behavior of this condensate is different to colder matter, how can we observe that? What will be the implications?
By studying caustics.
Clusters.
I'll do caustics. I'll explain that tomorrow.
Okay. So if there are no other questions, let's thank Pierre again.
Thank you.
And we have 20 minutes for a coffee break.